Attention is all you need. Part 0. Why this paper exists. This is Part 0 of our deep dive into Attention is All You Need, the paper that fundamentally changed how we think about sequence modeling and introduced the transformer architecture. This part is about understanding why this paper needed to exist in the first place. What problem were they solving? What had been tried before? And why did their solution matter so much? By the end of this session, you'll understand the complete context that made the transformer feel revolutionary, not just incremental. Let's begin with the abstract. Back in 2017, the most common models for tasks that take one sequence and produce another, like translating languages, were built using recurrent neural networks, or convolutional neural networks. Think of these as complex systems with two parts: an encoder that reads and understands the input, and a decoder that generates the output. The very best models at the time also used something called an attention mechanism to help the encoder and decoder communicate. Attention is basically the model's way of deciding which words to focus on when interpreting or producing the next word. But here's the key point the paper is making. Even with attention, these systems were still built on top of recurrence or convolutions, and that came with real limitations. RNNs typically process words one at a time, in order, which makes it hard to do lots of the work at once, and that can become a bottleneck when you want to train at scale. CNNs are more parallel-friendly, but modeling relationships between words that are far apart often means stacking many layers or using special convolution tricks. So long-range relationships are not always as direct. Either way, you run into scaling trade-offs. The solution? The researchers proposed something radical. They asked, what if we throw away the recurrent and convolutional parts entirely? What if we build a model using only attention mechanisms? They called this new architecture the transformer, and the core idea is that it transforms sequence representations through multiple layers where attention is the main engine, rather than recurrence or convolutions. Why it matters? The results. The paper reports that this wasn't just cleaner in design, it actually worked. On two major translation tasks, the transformer achieved higher quality while being more parallelizable, meaning it could process more of the work simultaneously rather than step by step. And critically, it trained much faster. Here are the concrete numbers. On the WMT 2014 English to German translation benchmark, they achieved a 28.4 blue score. BLEU, pronounced blue, is an automatic score that estimates how close a machine translation is to a human one. Higher is better. This improved on the existing best results, including ensembles, by over 2 blue. That's significant. An ensemble combines multiple models to boost performance, and a single transformer still beat them. Also, on the WMT 2014 English to French translation task, they got 41.8 blue score, establishing a new single-model state-of-the-art record. And here's the kicker. They trained this model in just 3.5 days on 8 GPUs, which the paper describes as a small fraction of the training cost of the best models in the literature. The model also generalized well beyond translation. They tested it on English constituency parsing, which is about understanding sentence structure, and it worked well with both large amounts of training data and limited training data. So at a high level, the abstract is telling us the old world was recurrence or convolutions. Attention was a helpful add-on, and the transformer flips that. Attention becomes the whole engine. Now, if you're thinking, fine, but what exactly was broken about the old approach? You're thinking like the authors. Part 1 is where they make the case. We'll walk through the introduction and the bottleneck problem. why step-by-step computation held back training, why GPUs couldn't be fully utilized, and why scaling to longer sequences became painful.